Yes, they are recording. So let's start. It's a big pleasure to introduce Professor José Arrieta from University of Madrid. José is going to speak about the distance of accretions of reaction diffusion equations in thin domains. And I expect the word shadowing somewhere inside.
Yes.
So I guess we will hear it. So please.
Okay, well, thank you very much. Thanks, Sergey Tikhomirov, for this kind invitation. I was listening to your talk in Brazil, like maybe a month ago or so. So afterwards, we talked via email, and then you kindly invited me to give a talk. Okay, what I'm going to talk is about distance of attractors of reaction diffusion equations in thin domains, okay? So let me start saying that this is a joint work with Esperanza Santamaria. And the work is based basically in 3 papers. 2 of them are dealing with estimates on distance of inertial manifolds. The first one is distance in the L infinity norm, and the other estimates in a stronger norm, like C1 theta norms. And the last paper appearing in Journal of Differential Equations is like the main bulk of the research, which is how to obtain the distance of attractors for reaction diffusion equations in thin domains. So let me start posing the problem, and let me say that we are going to consider a thin domain of this type, okay? So it's a rather general thin domain. Is R epsilon, which is like the points x, epsilon, y, such that x and y are in R0, okay? So you may think that this picture here, this like a bone-like thin domain is R0. And what we do is like we, with this epsilon, we shrink the bone so that it gets thinner and thinner and thinner, okay? So this domain obviously approaches as epsilon goes to 0 to the line segment given by the interval 0, 1 in 1 dimension, okay? So in this domain, we consider the reaction diffusion equation given here, okay, which is ut minus Laplacian u plus alpha u equal f of u, where if alpha is a positive number, you may think if you want that alpha is equal to 1, that is perfectly fine, there is no problem. And the nonlinearity satisfied that is regular enough. And I'm gonna consider a simple situation where f, f prime, and f seconds, all of them are bounded by uniformly by a constant for all value s in the real line, okay? So this is a very strong condition on F, but actually it is not very restrictive either, because since we are going to focus on the attractor of this equation, the attractor are uniformly bounded in L infinity, so we can always perform like a cutoff of the nonlinearity and obtain nonlinearities of this type. Performing this cutoff doesn't affect the attractors of the equation, okay? So it is very well known that the limiting equation is given by this one-dimensional reaction diffusion equation, okay? This one. So is Vt minus G 1 over G GVX x plus alpha B equal f of V, okay? With Neumann boundary condition. I forgot to say that in the reaction diffusion equation before, all the conditions I'm considering are Neumann boundary condition. This G that I have here is the n-1 dimensional event vector of the section of R0 at the point X. So if you imagine that this is R0, okay, and you fix a point X, so this is section of this domain, and Gx is the measure exactly of this section, okay? As I move X, this section varies, and obviously the measure also is varying also. I'm assuming that G of X is nice, is regular, okay? But doesn't need to be constant, so I'm not just considering a cylinder, okay? Also, this section has to be regular enough, and it has to be connected, okay? All right, so the first thing we're going to do is to pose all the problem in the same fixed domain R0, although with changing norms, okay? So if I, for epsilon fixed, let me see, I go back to the original domain R0 by stretching in the y directions, okay? Then we can change the problem P epsilon to this one. So this is the same problem, but now in R0, okay? In order to accomplish this, we do a change of variable that is stretching in all the y directions. By the way, the thin domain is not two-dimensional, it's in general n-dimensional. The natural space to analyze this problem is this norm, is this space with this norm, okay? Which is like the norm associated to the bilinear form in this problem. And this is the limiting problem, okay? For which we are going to consider these norms, okay? Observe that we have here some weighted norm, G. I didn't say, but obviously G is satisfies something like 0 less than G0 less or equal than Gx less or equal than G1, okay? So Gx does not degenerate at any point, okay? All right, so this allows us, first of all, to place all epsilon problem in the same fixed domain, and this is the problem in the limiting domain, the limiting problem. All right, so the limit problem P0 and the perturbed problem P epsilon can be written in an abstract setting as follows, okay? So I can write it like U epsilon T plus A epsilon U epsilon equal this nonlinearity, and here I have a different linear operator, different nonlinearity, and I have different spaces, ¿de acuerdo? Okay, so the operator A epsilon is basically this Laplace operator with a very high diffusion in the y direction, which is a self-adjoint positive definite linear operator with compact resolvent. And we denote by X epsilon L2R0, and say the fractional power space is X epsilon 1/2 is H1 epsilon R0. This is going to be my phase space, is the space where I am going to look for solutions of this problem, okay? Similarly, for the limit problem, I have, this is the operator A0, which is again self-adjoint, positive definite, with compact resolvent in the separable Hilbert space X0, L2 of 0, 1, and the X0 1/2 is H1, 0, 1, 0, 1, with the weighted norms stated above, with this weighted given with the function G. And the nonlinearities are given like this, which are basically the Minkowski operators associated to the function f, okay? So this is the general setting, and you can observe that the operators are posed, the equations, the systems are posed in different spaces, so we are going to need to translate, be able to have some operator that transform functions on one space into the other, okay? So this is how we do with we define an operator E, which is a linear operator, which goes from x0 to x epsilon. Recall that x0 is, for instance, L2 of 0, 1, and x epsilon L2 of R0. So what we do is we extend the function constant in the y direction, okay? So the extension of a function defined in 0, 1 to a function defined in the whole domain R0 is doing this way, okay? This is a nice linear operator, also transform x0 1/2 into x epsilon 1/2. The norm is equal to 1, and the norm in this space is also equal to 1. And we also have an average operator, which transforms functions defined in R0 in functions defined on 0, 1. How? Taking the average in the y direction, okay? And since the measure is different in different x, we have to scale here the measure, okay? Okay, so if we have these operators, then this M is also a nice operator, is bounded, has norm 1, and we can see that the composition of E with M gives the identity, while the other does not give the identity. Obviously, if I have a function defined in 0, 1, and I extend it to R0 constantly in the y direction, if now I take the average, I go back to the same function, okay? All right, so the nonlinear evolution operators, that is the subject of a study in this research, is given by these integral expressions that we call the variation of constant formula, which is expressed in terms of the linear semigroups, right? And this expression, integral expression, will appear the nonlinearity, okay? This is for the epsilon problem, so this is the perturbed problem, and for perturbed problem, and this is the limit problem. All right, so the fact that the nonlinearity, originally I said that f, the derivative and the second derivative is bounded, that implies that the system are dissipative systems. Do we have global existence of solutions for positive times for any initial condition in H1? So we have in a very nice situation where we have a dynamical system, okay? So this means that I can consider T epsilon T from this space H1 epsilon of R0 into H1 epsilon of R0, and this for each initial data, I have the solution starting at this initial data. So this defines a very nice dynamical system, and the same for T0 of T, okay? So I have T0 of T, which go from H1 of 0, 1 in H1 and 0, 1, okay? So it is very well known that P epsilon has an attractor that I call A epsilon in this space, H1 epsilon of R epsilon, okay? And the limited problem also have an attractor A0 in H1 of 0, 1, okay? Obviously, I can consider E of A0. Remember that E is the operator that transforms. We say H1, 0, 1 into H1 of R0, okay? So E H1 epsilon of R0, so that EA0 is contained in this H1 epsilon of R0. And I would like to compare these two attractors. So let's talk about convergence of the attractor. For this, we define the distance of a set A to a set B in this way. This is a non-symmetric distance, okay? So, for instance, this delta BA AB is 0 if A is contained in B. And with this, we can define this symmetric Hausdorff distance, okay? This is a different distance, which takes the maximum of both delta AB and delta BA, okay? And this is the symmetric Hausdorff distance, okay? So, well, from the convergence, by the way, I'm making a summary of many results that are known in the literature. Those results are taken from the work by Jack Hill and Jennifer Rogel that I will mention now in a couple of slides, okay? So we know it's not difficult to see that we have the upper semi-continuity of the attractors, okay? So this is saying that when I explore this distance of the set A epsilon into the inclusion of A0 in A1 epsilon for epsilon, okay, then this distance goes to 0, okay? So this is saying that if I have the attractor here A0, or with inclusion A0, for instance, this is the attractor, then this attractor A epsilon, it may be something like this, for instance. It is near EA0, okay? Upper semi-continuity. Yes, sorry.
Please.
Excuse me, Jose. Does this follow from some general results by Jack Hale?
Yes. Yeah, okay. In this case, Jack Hale, he proved in this paper. Let me mention this paper.
Okay.
Okay.
Thank you.
It is there. Okay. Yes, it is there. And there are several other papers that also obtain this upper semi-continuity of the attractors. Okay. Basically, it is if you have the continuity of the nonlinear semigroups and you have uniform estimates of the attractors, you can show the upper semi-continuity. Upper semi-continuity is in some sense easy to obtain. Okay. Okay. So, moreover, if all equilibria of the
I'm sorry. So may I continue
yes.
the question of Professor Pelugin? So if you speak, so you tell that this is kind of well-known, obvious, trivial. So then it is very well investigated area. Yes. So in that case, of course, a lot depends on the generator. So which you have of the semigroup. So what approximately conditions do you really need in order to be able to do this? So is it what type of condition it is?
For the upper semi-continuity, basically what I need is to the continuity of the nonlinear semigroups. Basically, this is it. So if I can prove that this nonlinear semigroup T epsilon T of U epsilon converges to T0 T of U0, for instance, obtaining an estimate of this following type: T epsilon T of U epsilon minus the extension of T0 T of the projection of this type, okay, in the phase space H1 epsilon of R0, and this is less or equal than a constant, probably times T to the minus some alpha. I mean, it doesn't need to be good when T goes to 0. Even you may have some exponential here, that's fine, times rho. Let me not call it rho because traditionally I think I call like eta of epsilon, and eta of epsilon goes to 0. And this is taken like the soup when U epsilon in the space is less or equal than R, and this eta may depend on R. If you have estimates of this type, right? And plus uniform estimate of the attractors. So the attractors, all of them are bounded, okay? Then you can get the upper semi-continuity of the attractors.
Okay,
Okay.
I see what, so I see what type of continuity you mean here.
Yeah.
Then usually it should be quite hard to establish this.
Well,
I would expect.
It depends. You need, I will talk about this now because basically to go to this, you need to have good estimates of the convergence of the linear semigroups.
Yes. I completely understand that for this you need some information about the, I don't know, spectrum or whatever.
Sure, yes, of the convergence, exactly.
And my question was about this more, yes? So.
Okay, yes, actually, I have a very short communication in the EquaDiff in Berlin that basically said that if you have a spectral convergence of the linear elliptic operators, then you have the upper semi-continuity of the attractors. Okay. So that's a very general. So what you are saying is completely right. If you control the spectrum of the operators, then you have the upper semi-continuity of the attractors.
But if you include, say, I don't know, transport term there, so kind of plus constant ux, would it work as well?
I will have to look at it. It depends. Okay. It depends on the operator. You can include some of them, but you have to be probably careful. Okay. Okay. But usually, I move in the realm of self-adjoint operators. But you can do something with non-self-adjoint. Okay. So this is the upper semi-continuity. So let me go to the lower semi-continuity. So if all now, in order to get lower semi-continuity, we need much more structure on the dynamical system. And actually, we can say if all equilibria of the limited problem on the attractor are hyperbolic, and hyperbolic we mean that they are all non-degenerate, so the spectrum, so P is hyperbolic if the spectrum of the linear operator at P does not have any eigenvalue with real part equals 0. Then, first of all, we can see that we have only a finite number of the eigenvalues, okay? And we can prove that for epsilon small enough, the perturbed system will also have exactly n equilibria. And they satisfy that they converge to the limiting eigenvalues, to the limiting equilibria, okay? And this, okay, so we have this convergence. Moreover, we get that the unstable manifolds, local unstable manifold of each equilibria converge to the local unstable manifold of the limit equilibria. And with this, it is not complicated to get the lower semi-continuity of the attractors, okay?
I'm sorry, one question.
Sure.
In this case, the attractor is a union of global unstable manifolds of this equilibria.
Yes.
And
this is a gradient system, so you are completely right. This is in the case where we have the attractor, the limiting attractor is the union of the unstable manifold of each equilibrium.
Okay. Usually in this situation, one also needs something like transversality condition.
Not transversality of the unstable manifolds and like this Morse-Smale.
And stable manifolds of other equilibria.
Not okay. Let me point this out. to obtain the lower semi-continuity, you don't need the transversality of the stable and unstable manifold. You need that to go a little far beyond. And it is in order to get that the attractor as C0 conjugate.
Okay, thank you.
Okay. So yes, this is important. So we don't need transversality here of the stable and unstable manifold. Okay. Okay. Let me also, for instance, tell you that a similar agenda to this one can be done not only for thin domains, but for perturbation of domains. If I have a domain fixed, and then I do a perturbation of the domain like this, okay, omega epsilon, even if the perturbation is not very nice, you can repeat the same agenda. And if you consider the limiting problem in omega, in general, it is not Morse-Smale, because if dimension of omega is larger than or equal than 2, in general, the reaction-diffusion equation is not Morse-Smale, okay? And you don't have the transversality of the stable and unstable manifolds. But even for this case, you can follow this agenda and you can obtain the continuity of the attractors. This is a paper that Alexandre Carvalho and myself did some time ago. Alexandre Carvalho from Brazil in JDE in 2004. Later on, I can give you more concrete reference if you are interested. Okay, so, but let me mention then that this, what I said before, it was done even in a more in a better way, I would say, by Jacques Hale and Jennifer Rogel in 1992 in this reaction-diffusion equation on thin domains. Okay, this is a famous paper that, and let me just explain what they did, because they followed this agenda, but a little different. They used inertial manifolds, okay? So let me say, the limiting problem, P0, okay, is a 1D reaction-diffusion equation. Okay, sorry. So this 1D reaction-diffusion equation, the linear elliptic operator, the eigenvalues have big gaps, and this allows you to apply the theory of inertial manifolds, so that for this P0, you have an inertial manifold M0. An inertial manifold that I have represented here like this is a manifold which is constructed globally, and that it is exponentially attracting, and that all the asymptotic dynamics of the limiting problem is contained to the manifold, okay? In particular, the attractor A0 is in this manifold M0, okay? Now, this manifold allows us to basically reduce the system to a finite dimensional one, because we can get a map phi 0 from Rm into the manifold, which is like, this is how the manifold is kind of constructed as the graph of some function phi 0. And then this allows us to reduce the system from the whole infinite dimensional manifold to the finite dimensional space Rm, okay? Now we have that they prove, Jennifer Rogel and Jacques Hale, that the perturbed system is a very nice C1 perturbation of the P0, of the limiting system. To be more specific, since P0, since the eigenvalues associated to P0 have gaps, and we have the convergence of the eigenvalues, then we have eigenvalues and gaps for the problem P epsilon. So if we have gaps for P epsilon, then we can construct inertial manifolds M epsilon also. Okay, so we have inertial manifolds for the perturbed system, which is high dimensional, and this is very unlikely. But in this case, if this is the perturbation of a 1D problem, we can get these inertial manifolds. So these inertial manifolds, which are also exponentially attractive, so this allows us also to reduce the system to a finite dimensional system, also in RM, okay? Now, they say, okay, since the manifold, since the finite dimensional system, reduced system in RM of the perturbed system and of the limit system are close in a C1 sense, they prove that, okay? Then, and using also, and now we use the Morse-Smale thing, is like, since the system, the limit system P0 is Morse-Smale, and Morse-Smale, you know, it means that we have that all the equilibria are hyperbolic and the stable and stable manifolds are transversal, okay? This transversality is very restrictive, but is very robust. So since the limiting system is Morse-Smale, then the reduced system in RM here is also Morse-Smale, okay? And the reduced system, the perturbed reduced system is a perturbation of the Morse-Smale, okay? So this is telling you that the reduced perturbed system is a C1 perturbation and therefore is conjugate to the limit system. Okay, so basically I take my systems that live in an infinite dimensional space, I reduce to inertial manifolds, and then I take it to the finite dimensional RM system. Here I have a lot of tools, right? And in particular, what Jacques Hale and Geneviève Rogel used is the fact that Morse-Smale are robust. So if the attractor of the limit system is given by A0, the attractor of the perturbed system in RM is given by A bar epsilon, then they are C0 conjugated. So, okay, we pass this information to the inertial manifolds, and since the inertial manifolds converge one another, we have the same C0 conjugate results between A0 and the attractors A epsilon. So they prove the continuity of the attractors and the fact that the attractors are C0 conjugate. Okay. All right. So let me what we are interested in trying to understand and trying to obtain estimates on the distance of the attractors. Okay. So this is really the subject of what we are interested in. So what about the estimates for the distance of the attractor? So there are results by Babin and Bishik in his famous book, in Attractors of Evolution Equation. They have this theorem that tells you about estimate the distance of the attractor. So they use basically the fact that the attractors are exponentially attractive, used by using this estimate, okay? And they are uniform in epsilon, because this alpha is uniform in epsilon. And they have also these estimates, which is not difficult to obtain through the variations of constant formula, basically, okay? So when they have this, they have, using that the system is gradient, that you have a finite number of equilibria and so on, you obtain a distance of the attractor of this type, where Q is alpha dividido alpha plus beta, okay? So this is one estimate of the attractor, but okay, this is one. There is another one very similar and done basically, almost basically at the same time, but also Jacques Hale and Geneviève Rogel in this paper, Lower Semi-Continuity of Attractor of Gradient Systems and Application, and they obtain an estimate of this type also. The estimate is a little worse because it depends on the number of equilibria, but the spirit of the proof is very similar, okay? So they use that they have a Lyapunov function and that they have a finite number of equilibria, and they study how the flow evolves with time, and they obtain these estimates for the distance of the attractors, okay? So we wonder whether these estimates are optimal, okay? This is the idea. Are these estimates optimal? The first thing, it seems like it does not look like optimal since the distance of the equilibria is smaller. It is not difficult to see that the distance between the equilibria of A0 and the equilibria of A epsilon is order epsilon. But here we cannot get this order epsilon, okay? So, okay, so in order to get good estimates of the attractor, the first thing we have to do is to obtain good estimates of the distance of the nonlinear semigroup of the dynamical systems. Okay, so this is a very much needed ingredient, is to obtain good estimates of the distance between the nonlinear semigroup, these two. Okay, so let me say that this is the nonlinear semigroup for epsilon, and this is for the limiting one. Okay, so eventually what I want to do is to subtract them. But if I subtract, I have the linear semigroup and the linear semigroup here, linear semigroup and linear semigroup here. And when I subtract them, I need to study the distance between these two linear semigroups. But these two linear semigroups are given as an integral in gamma, where gamma is a region in the complex plane of the resolvent operators, okay? So these are well-known formulas, okay? So it seems like, let me go to, to obtain the distance between these two, we have to compare the distance between these resolvent operators. But the distance between these resolvent operators, look, obviously with the M operator and the E operator here, to make it clear, we can express this in this way. This is like some algebraic identity, which is nice and is easy to obtain. We observe that this is bounded and this is bounded. So we need to estimate this very good, okay? So everything is driving us to obtain good estimates of this difference, which are the resolvent operator of the perturbed problem and the resolvent operator of the unperturbed problem, modulo these two M and E maps that relate that pass the information from one space to the other, okay? So, okay, so in this paper in the JDE that we proved with, we published with Esperanza Santamaria, we were able to obtain an estimate of this type, which is, I mean, it took us some time. It is not completely trivial, and it's in an appendix, and it takes some time, okay? So this is purely PDE approach, because we have to estimate the difference between the solutions of a PDE in the thin domain and the PDE in the limiting domain in the segment. Okay, but if we obtain this estimate for the resolvent operator, then, as I said before, we can get this estimate for the difference of the linear semigroups, which, okay, we have now here T minus 1 epsilon and T1 half, okay? So for fixed T, this is less or equal than epsilon, but I have a T minus 1 here, which is killing me a little. Moreover, using these estimates for the linear semigroup, we can go and with the variations of constant formula, obtain an estimate for the nonlinear semigroup, which is like this, okay? And the fact that we have a T minus 1 here implies that we obtain a log of epsilon here, okay? So this estimate is very important, and I have to admit that I would like to get rid of this log of epsilon, but we were not able to, okay? But as far as we can tell, this is the best we have been able to obtain the distance of the nonlinear semigroup, okay? So this is a very important ingredient, okay? So let me see how can we try to obtain the distance of the attractors. So obviously there is an approach using the fact that we have inertial of the limit system, and this is what I've seen in the works by Professor Perturbed and collaborators. And so the fact that the limit system P0 is a one-dimensional reaction-diffusion equation, we know that we have an inertial manifold. We have already said that, which is exponentially attractive and contains the attractor A0. So the existence of this inertial manifold, together with the fact that the limit system is Morse-Smale, is exploited to get good lower semi-continuity estimate in similar situation as the one that I've been for thin domains. And for instance, in the well-known book by Professor Perturbed and these other papers, basically, let me see if I'm explaining correctly. The idea, I think that the idea is the following. The system, the reduced system, the limit system reduced to the finite dimensional inertial manifold is Morse-Smale and has an attractor. And using the exponential attractivity properties of the inertial manifold and the ellipsis shadowing properties of Morse-Smale system in the manifold is extended to a neighborhood of the attractor in the infinite dimensional space, okay? So Morse-Smale system in finite dimensional spaces has ellipsis shadowing properties, and these ellipsis shadowing properties with the use of the inertial manifold is extended to a neighborhood of the attractor. And this guarantees the lower semi-continuity estimates of this type, okay? And this is not complicated. I think okay, yes. And then, so these are the lower semi-continuity, and the upper semi-continuity estimates are obtained through particular exponential attractivity properties of the attractor, okay? So this is the approach that I've seen in some of the works that I mentioned, okay? What we did is a little different, okay? We basically, what we did is let's follow the agenda that Jekyll and Genevieve-Rogel did, and let's try to understand, trying to obtain good estimates of the distance of the inertial manifold first, okay? So again, we know that the limit system has an inertial manifold, and this inertial manifold contains the attractor A0. We have the convergence of the eigenvalues and eigenfunctions of the elliptic problem in A epsilon to the elliptic problem A0. And this allows us to construct inertial manifolds M epsilon for the perturbed problems at P epsilon. Okay, these two manifolds will be regarded as graphs of the maps from Rm to H1 epsilon R0. And this is a nice reference to see constructions of inertial manifolds, a book by José and José. Okay, all right. So, and the idea is the following. Okay, again, we have a manifold M0, a manifold M epsilon, and they are constructed with these maps. Okay, so what we want to do is to obtain first good estimates on the distance of these inertial manifolds. Okay, so this is what we did in these two papers. Okay, in the first one, we obtained estimates. They are L infinity estimates on the distance of inertial manifolds, and these are C1 theta estimates on the distance of the inertial manifolds. We work out these two papers in a very general setting, not only for these particular thin domain problems, we gave abstract conditions to obtain these estimates, okay? But let me just summarize what we did, and is we have the spectrum of the operator A epsilon is given by this. We have the orthonormal eigenfunction of the epsilon problem, and we have the spectral projections over the first m eigenfunction, and over the rest of the eigenfunction, okay? So the limit problem, since it's one-dimensional, we have spectral gaps, okay? And okay, so let's assume that this m is such that lambda 0m and this distance are large enough. So, and this can be quantified explicitly, okay? So, but assume that this gap is large enough, and if the gap is large enough, larger than the Lipschitz constant of the nonlinearity and some other involved things, okay, we can construct these inertial manifolds, okay? But look, from the convergence of these resolvent operators, that this is something that we work out, and this is less or equal than epsilon, okay, we get that the eigenvalues converge, as you were saying before, Sergey, and we have these estimates of the projection on the finite dimensional space, okay? Remember that Pj0, Pj epsilon are the projection over the first m eigenfunctions, okay? And okay, again, we have this convergence of the linear semigroups, okay? Modulated by this projection over the finite dimensional and the infinite dimensional spaces, okay? So we get this epsilon and this L epsilon t, which is again this t minus 1, which is kind of killing us, because this is the responsible for later on to appear the log of epsilon, okay? But we can obtain these estimates, okay? So how to construct we follow the Lyapunov-Perron method to construct the inertial manifold. So we look for a function psi epsilon, which goes from the first m eigenfunctions to the other ones, to the orthogonal in L2, okay? Which is a fixed point of this map, okay? Where it appears the qm epsilon and so on, okay? So this is a standard way to obtain the inertial manifold, okay? And this p epsilon s is the solution that lives in the finite subspace, linear subspace, and is the solution of this, okay? All right, so now we want to transport all of this to Rm. Basically, this is Rm, okay? Because this is an m-dimensional subspace, and this is basically Rm. So using coordinates, basically, we can define the function phi epsilon from Rm into L to R0 as this way, okay? So given a z in Rm, okay, we put it with the eigenfunctions, the first m eigenfunction, and then we obtain that phi epsilon satisfies this, so, okay? And now the coordinate, this is a system in Rm, satisfy these ODEs, a system of m ODEs, okay? All right, so, I mean, this takes a lot of pages to write it carefully. I mean, it's extremely technical. So, but I want to come here because what I want now is to say, okay, I have the construction of the inertial manifold for the perturbed problem, and I have the construction of the inertial manifold for the unperturbed problem, okay? Here is the nonlinearity f epsilon, and here is f0, okay? So I'm calling this f tilde epsilon, f tilde 0, and then I subtract, and then I obtain something of this type and of this type. Here I have only the linear semigroup acting over the difference of this, but these non-linearities inside have the manifolds here. So when you subtract this first integral that I call it G1, it can be bounded like this. So this is a good part. Now, the other part is a little more not as good, and you can see that you have this, where this L epsilon t is this one, okay? And when you integrate something like this, the best you can get is something of this type, which is constant epsilon log of epsilon. From here, we get that the distance of the inertial manifold is again order epsilon log of epsilon. So this epsilon log of epsilon is accompanying us through the whole proof, okay? So the distance of the inertial manifold is order epsilon log of epsilon, okay? So, good. So let me mention also that, so that's why we call infinity, okay? So this is the sum of the distance of these maps, phi epsilon and phi 0 that define the inertial manifold, okay? Okay. Actually, it can be proved that these functions are a little more regular, are C1 theta from Rm into H1 epsilon of R0, if the nonlinearity F is smoother, okay? And this is taken by, for instance, in a paper by Chow, Liu, and Sell of smoothness of inertial manifold. Okay, with this paper and the way we have to compare the smoothness, compare the distance of the inertial manifolds, we can also obtain better estimates, not better estimate, estimates in better norms, which are of this type. And now we are losing something theta tilde for some zero theta tilde, which is in general less than 1. And this is what we did in our second paper of the inertial manifolds, okay? Okay, so this is how we get the distance of the inertial manifold, okay? So now, once we have the distance of the inertial manifold, I'm sorry, I'm extending too much the talk. I think that in like 10 minutes I will be done, okay?
15 minutes more. 15, 1-5.
Okay, thank you. Okay, so so now let us consider now that we have the inertial manifolds, instead of working with the flows, let's talk with the maps, okay? So let us consider the time one map of these flows, okay? So I'm talking about T epsilon at 1 and T0 at 1, okay? These are the maps that I'm talking about, okay? So I'm gonna call them T epsilon and T0, okay? Since we are dealing with gradient system, the attractor of the dynamical system generated by T epsilon D0 are the same, okay? So the attractors for the flows and the attractors for the map as dynamical systems iterating the maps are the same, okay? Moreover, we know that T0 is a Morse-Smale gradient system, and this is, I've seen this several times, and this is the appropriate reference. This is the famous work by Dan Henry, some infinite dimensional Morse-Smale system, defined parabolic differential equation, okay? That we are using constantly, okay? So now, the inertial manifold constructed above allow us to reduce both systems to Rm. This is basically the agenda of Jekyll and Genevieve-Rogel, but now we have good estimates on the inertial manifolds. So we have these two maps, T epsilon and T bar 0, which are defined as this one, okay? So T bar epsilon at the point Z is take a Z, take it to the manifold, apply T epsilon, and take it back to Rm, okay? And you have these two, okay? So since the distance of phi epsilon to phi 0 is like epsilon log of epsilon, and the distance of t epsilon to t0, we have also proved that it's epsilon log of epsilon, okay? So it is not difficult to see that the distance of these maps from Rm to Rm are epsilon log of epsilon. Okay, so moreover, since T0 is a Morse-Smale system, this is also a Morse-Smale system. Okay, so I'm in the situation that I have T0, a Morse-Smale system, and T epsilon is nearby. Okay, so is nearby in L infinity, and it's also nearby in C1, right? Because we have proved that the inertial manifolds are C1 closed, okay? But this is the estimate in L infinity, okay? So now is when we want to apply shadowing, okay? That you know very well. So this is the typical transparency that I put for people that are not familiar with shadowing, but we use Lipschitz shadowing, the Lipschitz shadowing property for negative orbits, okay? So we have the definition of a delta pseudo trajectory of a map T, which is one that goes backwards, and the difference of this is less or equal than delta. The concept of epsilon shadowing, and we say that the map T is Lipschitz shadowing property if there exists L delta 0 such that for any delta between 0 and delta 0 and any negative delta pseudo trajectory, this is L delta shadowed by a negative trajectory T in X, okay? So obviously, I'm not gonna spend more time in this. Okay, so this result that is by Professor Plyugin was very important for us. It's like if we have T from Rm to Rm is a Morse-Smale map which has an attractor A, then there exist neighborhoods in C1 of the there's a neighborhood theta of T in this topology, okay? And numbers L delta 0 such that for any map T prime here, T prime has the Lipschitz shadowing property in this neighborhood with the same constants. Okay? So we are going to apply this to T0. And with this, we can prove, it's not difficult to prove that if we have a Morse-Smale map which has a global attractor A, then there exists a neighborhood theta of T in this topology, so that for any two maps that have these two attractors, then the distance of the attractor is less or equal than the distance of the nonlinear maps, where this is the symmetric Hausdorff distance, okay? And this is using Lipschitz shadowing and is using the previous result and Lipschitz shadowing for negative orbits, okay? Because if I have a negative orbit for a negative orbit for T2 is a delta pseudo trajectory of T1 and vice versa. So these are completely symmetrical, okay? A negative orbit for T1 will be a delta pseudo trajectory for T2, okay? So with this applied to the thin domains, look, we have T bar epsilon and T bar 0 that have attractors A bar 0 by epsilon and A bar 0 in Rn, okay? So we have that this distance is less or equal than this distance in L infinity Rm to Rm. And this is given, as I said before, by this epsilon log of epsilon, okay? Okay, now, if it's clear that if we are able to obtain this distance these estimates for the attractors in RM, we can go back now to the inertial manifold. The distance between the inertial manifold is epsilon log of epsilon, so we obtain also the distance in this space of the two attractors. I'm missing here an E. This should be EA0, sorry. Epsilon log of epsilon. And say, basically, the picture is this. So I'm able to estimate the distance between these two attractors as epsilon log of epsilon, okay? The distance between these two manifolds is epsilon log of epsilon. And these maps, the distance between these two maps is epsilon log of epsilon. So everything is saying that the distance between this attractor and this attractor is epsilon log of epsilon. Okay? So this is how we apply shadowing techniques to obtain the distance of the attractors. We reduce to the inertial manifolds, study the distance of the inertial manifolds, and reducing the system to a finite dimensional one, we can apply the equivalence of Morse-Smale conditions to have Lipschitz shadowing for the system and for in the neighborhood of this one, okay? Let me just mention some final remarks is that in the estimates, the factor log of epsilon appears. And our question has been since then is, does it appear for technical reason, or is it really something that has to be there? So we don't know yet. My personal opinion is that this is technical. It shouldn't be there, but we haven't been able to get rid of this log of epsilon. The arguments, and most arguments that I've seen using obtaining good estimates of the distance of attractors use in an essential way that the system is Morse-Smale. So Morse-Smale means in particular that we have transversal intersection of a stable and unstable manifolds. So what about general gradient systems? So let us consider this domain, but not in one-dimensional thin domain, but a higher dimensional thin domain. So we don't know. The distance of what I'm saying here is that in general gradient system, we know that the local estimates are the same. So the distance of the equilibria is order epsilon. The distance of the local unstable manifold is order epsilon log of epsilon. And the distance of the nonlinear semigroup is this also, okay? So thank you very much. Gracias. Thank you.
Oh, thank you very much. Thanks.
Thank you very much also.
Thank you.
No,
Thank you.
okay, but thanks for the first time. Question? Comments, remarks?
I have a question returning to the previous slide.
Yes?
Yes. So you have a gradient system.
Yes.
You mean it has a global Lyapunov function, which decreases along trajectories.
Yes.
And every trajectory tends to a hyperbolic equilibrium.
Yes.
Yeah, I think there are approaches which would allow to get shadowing results without transversality, without this Morse-Smale structure.
Okay. I will be happy to know those.
Because you will have what we call C lambda structure, which some people here understand. And just now we have a young participant, a student of Sergei, Grisha Monakov. I hope he's here.
Yes, I am.
and he has some technologies for proving, for example, shading without Morse-Smale structure. I think we have what to discuss. We have what to discuss.
That is very interesting, actually. Yeah. Being able to obtain this Lipschitz shadowing without, for instance, Morse-Smale or without inertial manifolds, that would be good. Also, imagine that you have a Morse-Smale system, but you don't know inertial manifolds. You don't know whether the system has an inertial manifold. Can you get Lipschitz shadowing in the neighborhood of the attractor without inertial manifold? Is it possible?
I think that something like that is possible.
Okay. Oh, that's great. Okay.
I hope. I cannot guarantee just now, but this is what to be discussed.
Yes, definitely. Yeah.
So thank you very much for a very interesting talk.
Thank you.
Because it's, you see, it is close to our interests, to what we know, but there are some things which we do not know, and know they come from you just now.
Okay.
Well, thank you.
Well, William, let me tell you that I learned. Sorry.
One personal thing. Please tell my best regards to Professor Sanjurjo.
Okay, I will. Yes. He's a very good friend of mine. Yeah.
I have visited his seminar. I gave a talk at his seminar at your university. So
yes. Okay.
My best regards to him.
Okay. Thank you. And let me tell you that I learned a lot from your papers and from your book. It was very nice to read it, and I learned a lot.
Colleagues, more questions from students? From PhD students? So I have question actually. So in your case, you have an attractor 1D, yes, which is essentially, and when how to say, when you consider ND system, like you expect your attractor to be like a solution of 1D times constant. Yes, basically.
Say it again.
So you expect that in thin area, your solution is, so like I have two questions, yes?
Yes,
First
okay.
of all, if you go from 3D to 2D.
Okay, yes.
Can you do the same?
No, because I don't know that the 2D system has an inertial manifold. And I don't know whether the 2D system is Morse-Smale. So there are two.
Morse-Smale, so we
okay, I can do.
Sorry,
I can do.
We will teach you how to remove. Yes.
Okay.
Yes, but question of course of existence of inertial manifold is a strong one. Yes, so without it, you basically cannot do anything. So this is the.
But I can do one thing. I can tell you that the attractors behave continuously. That I know. So I know that the attractor of the thin domain converges upper and lower semi-continuously to the attractor of the limit problem, under the only hypothesis that the limit system, all the equilibria are hyperbolic, and it's a gradient system, okay? So, for instance, if I have a system of the type ut minus Laplacian u equal f of u in omega, okay, with du dn equals 0 in the boundary of omega, and omega is R2, or in general Rn, and I can perturb this to omega to say Q epsilon, which is omega times 0 epsilon, something like this, or even more general, okay? So we have omega, and we have here you have Q epsilon. Then I know that if the attractor, if this is all the equilibria are hyperbolic for this problem, I have convergence of the attractors. That I know. I cannot do estimates because I'm missing inertial manifolds and shadowing, and Morse-Smale. But if you are able to go to shadowing without Morse-Smale, that will be great.
Okay, and so since a question is here, I also will write more detail my previous question. So how I can annotate? I don't know why I cannot annotate. Because this is video, not.
You want to write my blackboard?
No. Okay. It
Yes.
will take infinite time in that case to change it. So if on this equation u sub t minus ut minus Laplace u, yes?
Yes.
If I would add the term, say b gradient u plus b gradient u.
Plus b grad u equal f of u.
Yeah, f of u or even 0. Yes, to be more.
Yeah.
But to feel better. Would something like this be applicable? You see, here you have a much greater invariant, so you don't have Morse-Smale in a certain sense.
No, right.
Because
right.
you have, at least if you're in the infinite domain, you have a lot of translational waves.
Okay, let me see. I think okay, basically
So this is transport term, yes?
Yes, but what you need basically is that the system is gradient or gradient-like. Gradient-like means that you don't need a Lyapunov function, but you need that solutions converge to equilibrium, okay? And that you need that the solutions, backward solutions, which are bounded, go to equilibria. So the attractor is expressed in terms of the union of unstable manifold of equilibria.
So you should put U, not S, of course.
Sorry. They are stable manifold, yes. So if you have this and you have the continuity of the nonlinear semigroup, which in this case, it is no problem because this is done through the variations of constant formula. And if you have the continuity of the local unstable manifolds, then you have the continuity, yes. I don't see much problem with this, even with a nonlinearity here, okay? So you can have
I
here.
think that the main problem is it true that you have attractor which is unstable manifolds of fixed points.
Yeah, okay, probably yes. Then yeah, if we leave the place of gradient systems, then in general for upper semi-continuity, things goes very well. Upper semi-continuity. Usually this is okay, always. Lower semi-continuity is not. Lower semi-continuity, you need a structure on the dynamical system to obtain lower semi-continuity. And this is basically what you need. I mean, apart from these cases, there are some cases, but it is not very well understood. But for upper semi-continuity, definitely you can. Because for upper semi-continuity, the only thing you need is to have the continuity of the nonlinear semigroups and that the attractors are uniformly bounded. But in any case, I may have a look at this and then I may go back and get back to you, okay?
Okay. Colleagues, more questions? Okay, let's then thanks Professor Arrieta again.
Thank you.
Yes, and we hope to see a joint paper soon.
Yes, okay. It was very nice for all of you. And thank you very much for this very, very kind invitation. And let's see if we can meet at some point when this pandemic finishes and we can travel and enjoy getting a cup of beer.
Right now we can on Zoom meet.
No, how are you doing?